Hello, greetings from my side. Uh, because nobody has joined till this time, so we shall wait for another 5 minutes because it's 3 p.m. already. So we shall wait for another 5 minutes, and after that, we shall start today's session. Thank you. All right. I believe we should proceed with our today's session. All right. I hope I am audible to you all. Somebody can
It's
confirm.
audible.
Yeah, thank you. Thank you. Thank you. Thanks a lot. All right. So today we are in our third tutorial session. All right. So as you already know, the instructor for this course is Professor Niranjan Sahu, and my name is Aditya Sharma, and I'm the teaching assistant for these tutorials. So total such 13 tutorials will be there, and in that series, this is our third tutorial session, live tutorial session. All right, and the name of the course is Fundamentals of Compressible Flow. So all right, so this is our third week, and the theme of this week was quasi 1D flows. All right, compressible flows. Obviously, compressible flows we are studying. So in that context only, this topic is quasi 1D flow or quasi 1D flow. So basically, in this topic, what there is, it is that basically we are concerned with 1D flow only, all right. But then it's a special type of 1D flow. Okay, so quasi means that though the flow is moving in one direction, but there is some catch to it, and that is that we will be changing as you guys must have gone through the lectures already. So in the lectures also, in the content of the lectures, it is mentioned that we are concerned with also the change in the area of a particular duct in which there is a flow, and then this, though this duct is like the flow moves in one direction in this duct, but then the area also changes while the flow proceeds in such a duct. Okay, so we shall look into that. All right. Uh, Before that, in the last uh, session, Yogesh had asked that why we just concentrate on isentropic flows. So I just briefly tried to look into it. So the answer I could get is that though in compressible flows, it's not always that the conditions will be isentropic, but for mathematical simplifications, we deal with isentropic flows, and it uh, for it for our purpose it proves as a reference for the flows that we deal with, the spectrum of flows and compressible flow we deal with different conditions, so it act as a reference for such flows. All right, Yogesh, this I could like
Yes, sir.
understand.
Yes, sir.
Yeah, yeah, yeah. So possibly that's the like correct or best answer for your question. Okay. All right. So also in this tutorial, what I have done is I have for different questions. So I went through your assignments. All right. So uh, what I did that I saw the topics that were involved in those questions, that these those questions that have been given to you guys. All right, so based on those topics I have some questions. All right, so I have categorized questions based on those topics. I have tried to like touch upon those topics. All right, and then numericals also in that fashion only. I have tried to arrange today's session in that manner. So let's see how it goes and how you guys find it. All right. So, but before that, we will proceed in that previous fashion only. So we will first see the topics that have been covered in the previous week, and then we shall jump on to our questions. All right. Okay then. So, so the first topic, the first main topic in your lecture 7 is effects of area change on flow properties. So, like I have already mentioned that we are dealing with the quasi one-dimensional flows. So the area change is in that context only has been introduced in whenever we see area change, it is in that context only. So we will be dealing. All right. So then next topic, with area change, how the properties change. So it was the main heading. Then under this, there were some few subheadings. So like one was expansion process on Mollier diagram. All right. So there was Mollier explanation of Mollier diagram, and then what is an expansion process in case of compressible flows. All right. So what is a compression process? So expansion, literally you can also uh, like visualize. So expansion is basically when there is the flow is expanding. All right. So compression, from the word compression, what do we take? It like comes into our mind that compression means increase in pressure. All right. So whenever within the flow there is increase in pressure somehow, so that we call compression process. And with respect to
Hello. Hello, sir. I think your internet is.
yes, yes, Yogesh.
Sorry, I can't hear you for a while. Maybe
All right. Now you are able to hear me, Yogesh,
yes, sir. Now I can able to.
and my presentation is also visible. All right.
Yes, yes.
All right. Thank you. So it's same with Ginny also.
Yes.
All right. Thank you. So So then I was explaining these two processes, all right, expansion process and compression process. So what I was saying is that this is in connection to the change in the pressures, all right, static pressure, change in the static pressures as whenever there is a flow and within the flow, if as the flow proceeds there is if increase in static pressure or decrease in static pressure, and linked to that if there is some increase or decrease in velocity. So such processes have been like discussed in these lectures, all right, based on Mollier diagram, all right, based on isentropic conditions. The graphs also have been shown. Okay. Then there were topics. All right. So there were two topics. All right. So this was adiabatic flow with friction. So in this, though there was no heat transfer, but friction was being considered. All right. And two such cases, two different cases were discussed. One was nozzle action and one was diffuser action. So basically, nozzle action means we want to increase the velocity. all right, and diffuser action means we want to decrease the flow from its current velocity. So and based on when friction comes into picture, so how do we understand such flows? So that was discussed in these lectures, all right. So then brief summary was given of this topic 7.1 that I have numbered, all right. And then this concept of this quasi one-dimensional flow was introduced, all right, and the governing equations linked to these were presented, all right. So if I am not wrong, the continuity equation was d rho by rho plus dp by p and dA by or something like this, all right. So also have gone through the slides, and for myself I also have prepared some notes, all right. All right, it was UAV, sorry. Okay. So this was rho AV. So the formula for mass flow rate is rho AV, right? So it is linked to that only, all right. So then momentum equation was also discussed, all right. P1A1 plus rho 1 U1 square A1 and so on. And then its a differential form was also introduced in the lectures. Then there was this energy equation. So this conservation of based on conservation of energy. So it was something like this. That implies H1. I'm just writing these so that we have just a visualization or revision of these formulae, all right. So in its differential form also it was given, this energy equation was given, and then a brief summary of the whole this concept of quasi one-dimensional flow was given, all right. So this was about lecture 7, and then in lecture 8, so I believe there are 2 questions, like straightforward questions are in the assignment on this topic only. Question number 1 and 3, all right. So this area velocity Mach number relation was given, all right. It's from the perspective of numericals. This is very important topic, all right. Also from the perspective of physics in compressible flows, it's also very important. So like in nozzle, how the flow behaves when the duct is either convergent or divergent, or if we are using both a convergent divergent nozzle, so how the flow behaves in such situations. So in such cases, this relation proves to be very useful, all right. Okay. So then there was effect of area change in isentropic flow, and so this was discussed, and then there were inferences based on this relation, all right. Different cases were mentioned or discussed, all right. Then after that there was this topic concept of supersonic nozzle, all right. So you want the flow to be supersonic as it exits your nozzle. All right, any type of nozzle be it, but you just want your flow to speed up. All right, and then this opposite to that was this supersonic diffuser. So in supersonic diffuser, like diffuser I have already mentioned, so we want to slow down the flow. All right, so how do we do it? So that has been discussed in this topic. All right, okay. So related to this D level nozzle, so there is one very important condition, that is choked condition at, so if D level nozzle nothing but is, so this is convergent section if the flow is moving in this direction, convergent section, and this one is divergent section. Okay, so choked mass flow rate. So this choked mass flow rate. So mass flow rate in choked conditions is also the maximum mass flow rate that is possible when we are using such convergent divergent nozzle, which is also known as D level nozzle. All right. So that is, the name is based on the given, based on the inventor of this particular nozzle. All right. So choked mass flow rate has been discussed, and the what is the choked condition? Basically, at choked condition, this throat gets choked. This is the throat of the nozzle, so it gets choked. All right, and this is very like clear from the thing that if there is something is choked, then like further the mass flow rate in that duct cannot be increased. So the choked condition corresponds to the maximum mass flow rate that this duct can give out. So this topic was discussed, and then so based on this area Mach number relation, uh, these gas property, this gas property table has been discussed. So in this area Mach number relation, so there is this Mach number and area relation. All right, so it gives two solutions of Mach, and the one solution is subsonic and the other solution is supersonic. All right, so this topic was discussed. Okay, all right, so these were the topics which were discussed in the lectures of week 3. All right, anything you want to add to this discussion up till this point? Yes.
No, sir.
Okay. All right. So I believe then we should proceed forward. with the questions. All right. Okay then. Okay. So we have our first question of session 3. So this is our topic. All right. This is our topic for this question: area velocity Mach number relation. So in a supersonic flow, the decrease in flow velocity. So we have been given two things, all right. There is this supersonic flow, means m is greater than 1, right? All right. And then the decrease in flow velocity. So flow velocity is decreasing. So we have been asked that it is associated with what behavior of area. All right. So we have only two options. So based on this area velocity Mach number relation, yes, what's the area velocity Mach number relation? It is dA by A equals to m square minus 1 du by u. All right. Please check.
I think decrease.
Decrease. All right. So let's see how. So because m will be greater than 1, all right. So this thing will be positive, right? Right. And it is given that the velocity is increasing. So this part will be negative. All right. So if we multiply a positive with negative, we will get what? If we multiply these, we will get a negative. All right. And our negative is this, which means what? The area will decrease. All right. Yes. So if we have this duct and the area is this is what it means, right? So if we have this duct and the area has decreased this way, all right. So basically it's if the cross section is circular, all right, so it will be like this. So in that scenario, if the flow is supersonic, so this will be what? The flow will velocity will decrease. All right. Okay. So let's move to our next question. So the answer is B. All right. This is the answer. Okay. Okay. So this topic is expansion process in Morlier diagram. So let's see, because the question says in case of nozzle action. So nozzle action has been mentioned to us, all right. Which event must happen in the flow direction? So I have already discussed what a nozzle action means. So in that case, which event must happen in the flow direction? So let's see the options first. Okay. All right. So you guys have to answer me this question. What a nozzle does, and then also whether it's a expansion process or compression process, because if velocity increases, what happens to the static pressure? All right, and what happens to static pressure decides whether your process is a compression process or an expansion process. Okay, so in this way you can try to answer this.
Sir, option A.
Option A. All right. And what does Ginny says say? No
A.
response. A. All right. Right. So you both are, I believe, correct. Yes, you both are correct, right? So this has already been discussed. Right. So if say the nozzle, all right, and if the flow is subsonic, in that case it will be for a like this combination of m less than 1 and a convergent duct is one of the examples of this nozzle action. So in that case, obviously the flow velocity increases, but with that, like it happens at the cost of pressure decrease. All right. So you both are correct. Option A is correct. All right. Okay. So let's see our next question. This is also based on this area velocity Mach number relation. All right. So far, okay, okay. Yes. So these are options. These are our options. All right. So if Ginny wants to comment on this, DYU. So if M is 1,
0.
yes, it will be nothing but 0. So here, two these assignment questions, question number 1 and 3 are based on these topics. So these are not exactly or in some way they are related, but they are related in terms of the topic on which they are based. So I believe we are discussing that topic or some equations related to that topic. That should be helpful to solve the assignment, right? This is the idea behind today's this introducing this topic and question based on that topic. All right. Okay. All right. Let's move ahead. Oh, sorry. It should have been B. All right. The mistake. Okay. This is P. All right. Okay, then let's move on to our next question. This is based on choke flow condition. All right. So the question number 4 is, in a convergent divergent duct with here. So this is CD duct has been given, and it has been told that this is air with gamma equals to 1.4 flow under choked flow condition. So choked flow condition has been given. The percentage decrease in density at the throat of the duct. So this percentage in decrease in density at the throat of the duct with respect to density of atmosphere. To density of atmosphere is all right. Okay. Yes. So how do we solve this?
So in last tutorial we have used one formula now. Rho naught by rho equal to 1 plus rho minus 1 by 2 m square of whole of 1 by rho minus.
Yes.
That one we can use, I think. Maybe we can
All
take
right.
rho naught as 1.4.
Rho naught as?
Sorry, with atmospheric air, we can take the density of air, atmospheric air as rho naught. Or rho,
Okay.
I have.
Okay. So that is also because if we can get the ratios right. So if we can get the ratios, we don't want the exact this number of this density. The ratios will work. So if we have the ratio of density at the throat to this atmospheric density, so that would suffice, right? That would be sufficient, right, Yogesh?
Sir, in the case of which one I know to take rho naught, that stagnation pressure, which one will be atmospheric air or?
Yes, obviously,
Oh,
because this the formula will give what? The formula is if you see the formula is this formula.
stagnation to
Yes.
static.
I tell you. So I remember it this way. So this is m square, right? This is the formula, right? And for rho naught by rho, it is T naught by T 1 by gamma minus 1. This is the formula, right?
Yes, sir.
Yes. So this is the formula. So this is the static pressure, all right. In any case, if you want the pressure at this throat, so that will be static pressure, all right. Because stagnation pressure, total pressure, if we consider isentropic conditions, and if we consider that there has been no loss of total pressure, all right. Because stagnation pressure and total pressure, they both mean they both are one and the same thing, all right. So to to have rho naught at throat doesn't mean anything, all right. So here we are concerned with the static properties at the throat, or static density at the throat, and we have been given this rho naught we have been given, and we need to find just this rho star, all right. All right, Yogesh.
Sir.
Okay, so we can just try to work this out, all right. So this is our question number 4. solution. Okay, so let's do it. Let's try to do it. I'm also doing it. So we have. Yes.
So can I take m equal to 1 because it's a choked condition? Generally m equal to 1.
Yeah, obviously that is how we are going to solve this. All right. So if you see, I had written this T naught by T equals to 1 plus gamma minus 1 by 2 m square. All right. So gamma has been given as 1.4, right? By 2 1. So this is nothing but what 1 point plus 0.2, that is 1.2. So this is all right. Sorry. So rho star is what? T naught by T star 1 by gamma minus 1. That is 1.2 1 by 0.4. All right. But we are concerned with the ratio of rho star by rho naught. All right. So because we have been asked with respect to this atmospheric pressure, all right, how much this density, static density, I believe, has decreased. So if we see, this is 1 by 1.2. This will be like this. So let's try to calculate this. So this is 1 divided by 1.2 and this is 2.5. So 1 divided by
1.577 if we take 3 decimals.
Wait. So this comes out to be how much did you get, Yogesh?
So 1.577.
1.577.
Yes, sir.
This value. What did you calculate? Rho star by rho naught or?
No. 1.2 of 2.5. Like 1.2 power of 2.5.
Just yeah. So divide 1 by this value. Do it.
.634 or yeah.
And what is Ginny getting?
0.6339.
Right. Okay then. So I'm also getting like these values. All right. Close to this. So what does this mean, that rho star is nothing but of this? So this static density of the air at throat has decreased. All right. So it has decreased to 0.6339 or just say 0.633. All right. Because we have to find percentage, so we'll take three digits after this decimal. All right. So So this has reduced to this from rho naught. All right. So when there is no flow, all right. So stagnation, static, they both are same. All right. But then, all right. So, Ginny, could you please switch off your mic? Yes, thank you. All right. So this density has reduced to this. So I was saying that at this reservoir or at the initial condition when there is no flow, right? This stagnation condition, at this stagnation condition. So static and total are one and the same. All right. But then when there is a flow, so static and stagnation are not one and the same. All right. So in that case, the static has reduced. All right. So reduced to this. All right. But we have been asked that by how much it has reduced. All right. So reduced density will be rho naught minus 0.633 or 634. All right. So this comes out to be 0.366 rho naught. All right. Am I clear? All right. So what I have been asked, we have been asked that by what percentage? Like, all right. So percentage decrease we have been asked, which is it has decreased by this divided by original. All right. Into 100. Rho naught into 100, which comes out to be 36.6%. So this is our answer. This is our answer. Okay. I hope this is clear. All right. So this was our fourth question. Okay. So our answer is 36.4. Okay. So this question was based on choked flow. All right. So what we did in this question, we used these isentropic, one of the three isentropic relations, right? And then we used M as one in it, as Yogesh also pointed this out. All right. And then we moved forward to solve this in this session. Okay, so let's see our next question then. Okay, so this question is based on this concept of supersonic nozzle and supersonic diffuser. So this I have briefly touched upon this in the topics covered. Okay. So either it was in lecture 8 or lecture 9. So in a D level nozzle, the maximum mass flow is reached when the Mach at the throat is. I have already discussed this. All right. So what's the answer to this question?
One.
Yes. And Yogesh, what do you say?
Sir, 1.
Yes. Okay. All right. Both are correct. So the answer is B. Okay. So I hope there is no doubt in this question. Right.
Sir, can you just give some insight on this? It will be better.
Sorry.
If you can explain this question very.
Yes. Sure. Why not? Why not? So this is our D level nozzle. All right. Something like this and something. This is our throat. So let's say the flow is in this direction. All right. So this is our throat. Okay. So what is mass flow rate? Rho A V or U, right? Okay. So what happens is, so this mass flow rate comprises of three things, right? There is density of the this air or gas we are dealing with, and then there is velocity linked to that, and then there is uh, area linked to that. All right. So let us suppose this is 1 and this is 2. All right. Rho 1 A1 U1 equals to rho 2 A2 U2. So three parameters are there in this mass flow, like how we calculate mass flow, right? So the how to explain it? So when the flow reaches a throat, right? So if there is this, let us suppose there is this subsonic flow. All right. So if this subsonic flow enters into this convergent section of this D level nozzle, all right. So if we see the area Mach number, this velocity relation, so it obviously points out to the fact that the velocity here will increase, right? So if we keep on decreasing the area, if we keep on decreasing this area, all right. So if we move in this direction, so area obviously is decreasing, all right. But then if we just keep on decreasing the this area, that doesn't mean that our this flow will keep on accelerating to whatever extent you want to like decrease the area, all right? So as this velocity reaches to a point that the Mach of the flow is 1, in that case it's not possible for the flow in terms of its potential, it's not possible for the flow to further accelerate on this uh, on decreasing the area of this duct, convergent duct, all right? So in that case what we prefer is that when if we further want to accelerate, because this happens in this uh, real applications also, so this is the only function, this is the main function of, this is the idea behind such nozzles. So if we want to further accelerate this flow, then we choose this divergent section, all right? Because if we see the again come to this area, Mach number and velocity relation, so for this supersonic flow, if you see and work this out, so for a this divergent section, the flow velocity increases with it, all right? So that's why we choose this divergent section. But then if you see this uh, uh, velocity or Mach at 1, so beyond this point you cannot increase the mass flow rate as far as the mass flow rate is concerned, because in the mass flow rate, though we can alter these two things, all right? Maybe if you want to increase, maybe let's say this u2 is greater than u1, all right, all right, but then this area, if you see, let us say a2 is greater than a1, all right? So these two terms, this a2 and u2, all right? So I'll write here, all right? So a2 and u2, if you in combined, if you see, they are u2 and u1 and a1. So if you multiply these two things, all right, so obviously this will be greater than this, in case like if you have a subsonic flow. I'm just discussing it based on this particular example, all right, just for the sake of discussion. So it can be this m can be greater than 1, and then there will be scenario will be different, but just for the sake of discussion I'm just sticking to this particular scenario, all right? But then we have these two this one parameter, we are left with this rho, all right? So rho will have to adjust itself in such a manner uh, that the mass flow rate remains conserved, all right? So in that case, obviously rho 2 has to be less than rho 1, all right? So this discussion I could pull off on this particular question. So now you guys tell, what do you want to ask?
No, sir, it was clear.
All right. Okay. All right then. Okay. So the time is 4, I believe. All right. So we should take 5 minutes rest and then proceed further. Is it fine with both of you?
It's okay.
Yes, sir.
Okay then. Let's take a 5 minutes break and then move ahead. Okay, then let's move ahead. If you guys are online again.
Yes.
Yes, sir.
All right. Okay. So next question is based on diffuser action. All right. So in a diffuser action, what should be minimum? All right. So we will answer this question based on the options that have been presented to us that are in our hand. All right. So first of all, let's see what are the options, and then the context to this question would be more clear. All right. Right. So we have four options. So here the question is concerned with the pressure. So either it is answer is in static pressure or it is in total pressure. So first of all, we should know what a diffuser action is. All right. And once we know that, then we must be able to relate to that the pressures. So what is our target? All right. Okay.
Static pressure.
Static pressure. All right. And what does Ginny say?
I'm not sure.
You're not sure. That is fine. That is fine. Okay. So I'll just give the context further. All right. So in my bachelor's, so I did this intern in one of these laboratories of DRDO. All right. So there they are developing pulse detonation engine. So we were given this assignment, or I should say this assignment only. So to like see the calculations of this intake of this particular engine. All right, very basic like mathematics based on these uh, based on the concepts of these gas dynamics. All right. So here also I must tell you that I work in this gas dynamics laboratory of this IIT Guwahati. All right. So what I was saying is that, so from this question only, because there also it was told to us that you have to move in such and such fashion. So from this answer, it just clicked my mind. So what happens in these engines is that at supersonic velocities. So this one of the scientists there under whom I was working. So he told that at supersonic velocities you have to uh, design your this intake of air in such a manner, if it's a air breathing engine. All right. So you have to design it in such a fashion that you should be able to slow down the air, because if you take the intake of air at supersonic velocities, then it won't be uh, possible to combust the engine, the fuel in the engine. All right. So for that matter, diffusers are designed. All right. So one such like task was given to me and my friend. All right. So very small task. All right. So this in that, but we have to consider what we have to take in mind, that when we are trying to slow down this flow, we don't want the flow to lose its pressure. All right. So this question is in that context only. So in the this task of a diffuser is to slow down the flow, all right, but then that should not be done at the cost of losing total pressure of that flow, because it's obviously a potential, all right. The pressure is obviously a potential, and you don't want to lose that, all right, because in engines this pressure is very important. You cannot lose pressure, because it then will affect the somehow it will affect the total efficiency of your whole engine, all right. So that should be very well taken into care, right? This also this line is in one of the slides of one of the lectures, all right. It's not that I have taken it totally something from that has not been presented to us to you guys in these lectures. Okay, there's one line in one of the slides, this that you have to take care of the total pressure, that you cannot lose the total pressure too much. All right, we were given, if I correctly remember, that the total pressure loss cannot be more than 4% or 0.4%. It was something like that. Okay. So this question is in that context. So for diffusers, like in real life, like how do we see a diffuser's function? All right. So total pressure loss. All right. So the answer to this is total pressure loss. Okay. Then this question, next question we need to work out. Gas with reservoir pressure of 20 bar exits a D level nozzle at 2 bar. So calculate the exit Mach number assuming the specific heat ratio to be 1.47. So please just work this out. Very straightforward question based on isentropic relations, because in your assignments, question number 7 and 8 are based on isentropic relations only. All right. So it should also serve as a hint. Obviously, we cannot discuss the, as I've already told in the past session or sessions, but then question number 7. All right. Yes, please work this out. In a very simple and straightforward language, I have presented this question. Question number 7. Solution. So P naught is given to be 20 bars, right? P exit is given to be 2 bars, all right? Then we need to find what is this Mach at exit? This is the question, right? Yes. So we know P naught by P is gamma minus 1. All right. So what I'll do, so if I say a equals to b square, all right, I'm just giving a mathematical operation, and if I take root on both the sides, all right, what will happen? A1 by 2 will become b. So these two things, this and this, both are same. All right. What I did an operation of, I had 2 and I just wanted it to be 1 somehow. This exponent of b, I wanted it to be 1. So what I did, I did this operation of 1 by 2 on both the sides, and this is how I got this uh, b. All right. So same thing I'll do here only. All right. I'm sure you guys must be just knowing this, but just I wanted to just explain it like further. So I just wrote these like gave this example. All right. So same thing I'll do here. All right. So I'll give this operation, but let's decide what should be the exponent here. All right. So this was, we have at present we have this. I want, because I want this m thing I want. All right. From here, this is my question. So what I'll do, I'll multiply with gamma minus 1 by gamma here to the whole, and because I did this on the right hand side, so same has to be done on the left hand side. All right. So this becomes p naught by p gamma minus 1 by gamma equals to 1 plus gamma minus 1 by 2 m square. All right. Okay. It becomes this. All right. Let me just switch on my light. All right. Wait a second. All right. Okay. So this, because we are concerned with this exit MAC. All right. So we have P naught as 20 and P is given as 2 bar, right? And gamma is 1.47, if I'm not wrong, right? So 1.47 minus 1 divided by 1.47. 1 plus 1.47 minus 1 divided by 2 me square. So this comes out to be 10. 0.47 divided by 1.47 equals to 1 plus 0.47 divided by 2 me square, right? Now just work this out and find me. I'm also working this out. Nice. 2.0879 minus 1 equals to me square. 9. Oops. It should have been 0. me square. All right. 11.2 divided by 0.47 me square. Okay. So
So is that the answer is 2.151?
2.15, yes, I'm also getting 2.15 in my rough work, what I worked out. But here I'm getting something else. What are you getting, Ginny?
$2.156.
Yes. So I did mistake somewhere. -1. Oh. Right. 2 into, wait, 2 into 1.08. Right. So this comes out to be 0.6293, implies me square equals to 4.6293, and which means me is 2.149, right? Or 2.15. Answer. You guys are correct. Okay. Now, let's move on to next question. This is our answer already. This is clear, right? So,
Yes.
in question, yes. All right, thank you. In question number 7, if reservoir temperature is 3000 Kelvin, then calculate the exit velocity. Oh, this should have been capital. I'm sorry. Take R equals to 287 universal gas constant in SI units. Right. Then you calculate the exit velocity. Yes. From the previous question, at the exit we have exit Mach number. Okay, and we know Mach is velocity of the flow divided by the speed of sound in that medium. All right, in that flow. So, question number 8, solution. Right. We can do this, right? So we want this exit velocity. Velocity UE. We don't know this, but we have calculated this back, right? Exit Mac at exit point. Also, Mac is velocity by speed of sound, right? So in our context, it is UE by AE. Sorry, right? So 2.15 equals to UEAE. Now, what is the formula for speed of sound?
So square root of rho r.
Yes. Okay. Thank you. Thanks a lot. Right. Right. So this gamma has been given to us and R is also given to us. Then exit, what has been asked? TE, we don't have TE. Or do we have TE? See the question. Reservoir temperature is given. TE is not given. Okay. By mistake, just don't put 3000 as TE. So we need to calculate TE. How do we calculate TE? From the, as this heading of this topic of this question, you must have noticed is isentropic relations, right? So shall use this and square, right? So this is 3000 divided by TE equals to 1 plus 0.47 divided by 2 and ME from the previous question is 2.149. That's right, 2.149 implies 3000 by TE is equal to, yes, calculate this. Let me just reconfirm this. 2 point. Yes, I believe I have done the calculation right. 85. Three thousand by 2.085. All right. Just confirm this if you guys are also getting the same.
Yes, 1436.
Okay. And what is Yogesh getting?
Same.
Same, right? So then till this point, we are clear, right? Yes. You want to see the screen? Yes, Ginny?
No, what?
You wanted to
No,
say
no.
something?
Okay.
No.
No.
All right. Okay. Okay then. So topic is area velocity Mach number relation, expansion and compression process on modular diagram. Okay. For an isentropic flow, the increase in area in the
So that
direction of
question, last question finished. Because
yes,
we
I
need to
believe.
find the exit velocity, no?
Oh. Oops. Right. Okay, sorry. Thanks for taking care of this. Okay. So we have TE, right? So gamma RT, right? So sorry. So exit velocity.
1675.
Okay, right. $2.149. Yes, now it's complete. Right?
Yes.
Okay. Then we have this area velocity Mach number relation. Topic is area velocity Mach number relation, and then expansion and compression processes on modular diagram. So for an isentropic flow, the increase in area in the direction of a subsonic flow leads to, yes. Let me just check if I have options for this. Yes, I have options for this. Please answer this question.
So D option.
Okay. Yogesh says D option. What does Ginny say?
B, degrees in static enthalpy.
Okay. Okay. So Ginny says this. Yogesh says this. Okay. All right. So the case is we have this flow, subsonic flow. The area has increased here, right? If the flow is from left to right, right, the area has increased here. All right, from this initial point to second point, the area has decreased, and in the starting, this is subsonic. All right. So if area velocity Mach number relation has to be used, this is going to be a what will happen to the static pressure? What will happen to the static pressure here? If we move from first position to second position?
Pressure decreases.
Pressure decreases. Okay. Okay. And what does Yogesh say?
So pressure decreases.
Pressure decreases. And what happens to the velocity? Okay. Let's see this again.
Increases.
Increases. Okay. Yeah. So dA by A is positive, right? This is positive. This is negative. This has to be what? Negative. Only then it will be mathematically correct, right? So this means the velocity will decrease. Decrease. That means pressure. Static pressure will increase. Right. So enthalpy basically, as these discussions on this topic says that enthalpy is a potential. All right. So, oh sorry, there is mistake in this. It should have been decrease in Mach number, and this should have been the right, because its potential has increased. All right. This is what I can deduce from what we have in our hand. It should have been A and C. So I have given wrong options. Okay. Anyways, so yes.
I think that it will have a decrease in both static enthalpy as well as the match number because area is increasing. Variance is positive.
But it's not just about area, Yogesh, all right? It's about what type of flow it is, whether it is subsonic or supersonic. Just because area has increased or decreased, just based on this information, we cannot deduce whether the static enthalpy has increased or decreased. We need to see in terms of whether its potential has increased or decreased. All right. So this has also been discussed in these topics. All right. Expansion and compression on Mollier diagram. So if the if the velocity increases, right, or if the Mach number increases, the static enthalpy decreases. But if there is decrease in Mach number, then there should be increase in the static enthalpy. This is what I understand from the content also. All right. Okay. But if you have some doubt on this, we can just go through this.
Because in my notes I have written like in the direction of supersonic flow, the static enthalpy will increase. In the direction of subsonic flow, the static enthalpy will decrease. As the
Okay. Okay. All right then. But then in the direction of supersonic flow, what will happen?
So static enthalpy will increase.
Will increase. But I believe that there has to be this area thing has to be in the picture.
Yes, that area is in the picture. It was clearly that both the cases Mach number will decrease. But in the supersonic case, when the area is increasing, then static enthalpy will also increase. But in subsonic case, it will decrease. Static enthalpy will decrease.
Okay, okay, then I'll just look into this question again, all right? This whether the static enthalpy increases or decreases, but this is sure that the Mach number will decrease, all right?
So that was sure.
That is sure, right? Okay, I'll look into it, and then we shall discuss in the starting of next session, all right? Question number 9. Let me just note this down. Question number 9. Yes. Okay. All right. Okay then. Then let's jump to next question then. We shall see this in the next session, all right? Okay.
Yes, sir.
So this is next question. Right. What is the maximum speed in meter per second that can be achieved by accelerating a stagnant air whose universal gas constant has been given at a standard sea level of this and this condition, all right? So this has been given to us. Okay. So the topic is energy equation, all right?
Can you show the question one time?
Yes, yes, please. Yes.
Sir, done.
Done. All right. This is okay. All right. Let's solve this. We have been given R equals to 287 joule per kg Kelvin. All right. Then P naught is given 101325 Pascal. Right. T naught is given 15 degrees Celsius. That is 273.15 plus 15 Kelvin, which is nothing but 288.15 Kelvin. And what does the energy equation say? H1 plus U1 square by 2 H2 plus U2 square by 2. Okay. So the question says that maximum speed we want, and we want to this accelerate this stagnant air, right? All right. So if the H is written as Cp T naught, right? Let us say this is stagnant air, for stagnant air, and this is for maximum velocity. Like two scenarios we have. Sorry. Okay. Cpt naught equals to Cpt plus V max square by 2. This is it. But if we want that the whole this potential of this air gets converted into its velocity, then we'll assume that this is possible when t is 0, which is hypothetical, but it's not possible, all right? Because this has been asked in the question only, that's why for the sake of question only we are doing it, all right? Otherwise, in reality, it's not possible to reach 0 Kelvin. What is Cp? Cv is 1 by gamma minus 1 R and Cp is gamma by gamma minus 1 R, all right? Yes. T naught, what is T naught? T naught is given to us, right? Okay. Two gamma by gamma minus 1 R T naught equals to 2 into 1.4 divided by 0.4 into 287 into 288.15 whole under root. Work this out. This comes out to be, yes, 2 into 1.4 into 88.15. Okay, divided by 4.
760.85.
Okay. I'm also getting this. What is Ginny getting?
$237.
Just check.
I will check it.
Sir, can you tell that we have taken t equal to 0 now?
Yes.
Yes. In which part of the question it has that given that t equal to 0? So I have read the question, I can't find it.
This question actually was from one of the previous this
No,
previous
not like that.
assignment.
Not like that.
No, I get you're asking that it is in which of the slides. All right, so this is directly, I believe you won't get this in slides because I also haven't come across this particular information. But then, because this question was in one of the previous assignments, and this is linked to energy equation, so I thought I should discuss this. All right. But if this doesn't click you that the whole potential has to be converted into the maximum velocity, then I believe one won't be able to answer this question. Okay.
The thing is, sir, is it we taken t equal to 0 because they have given that at standard sea level condition?
Because what?
Because in the question they have given it at standard sea level condition. Because of that.
No, standards here, T0, T0 is, it's a very extreme temperature. So standard C is not linked to it. Even these superconductors, when we discuss superconductors, they have some materials show this superconductivity at very low temperatures. All right, it's not 0 degrees Celsius, it's 0 Kelvin. All right. Yes, so it is not linked to this sea level condition.
Okay.
Okay. Even the superconductors, some materials show superconductivity at very low temperatures. I don't remember the correct figures, but if I roughly remember it, it's 27 Kelvin or something. I remember I have read it. All right. But below that, going below that is very tough. All right.
Yes, sir.
And if we can go to this temperature, is also, I don't believe that it is possible, or I haven't read it in this way that it is possible. Okay. Much also I don't know about this particular subject, but yes, generally we don't discuss such low temperatures. So superconductivity people, they must be discussing these low temperatures. All right. Okay. Okay. We have hardly 5 minutes. All right. So this question was over. All right. Ginny, could you just?
Yes, I got the answer 760.85.
Okay, okay.
Yes, I missed the
Let,
value while calculating. One value
no
I
issue.
missed it as.
Okay, okay, no issues. All right. So let's move ahead. So 3 more questions. Okay. Area Mach number relation is dash in nature. Okay. Tell me this. Yes, 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 yes. Fast. Right. Area Mach number relation is dash in nature. Check this out
Quadratic.
then. Okay. Yes. So it is quadratic in nature. All right. So I was earlier also I was telling this you get 2 solutions out of this. One is subsonic and one is supersonic. Okay. When you solve this. So this is throat. A star is for throat and A is for the area we are concerned with. So if like let's see if this is a nozzle, then at symmetry there can be 2 such areas which have same area, 2 cross sections which have same area. But then if there is some flow moving in this direction in one particular direction, so at one cross section there will be subsonic flow and at one there will be supersonic flow. All right. If we work some numerical based on this out, so we will get 2 solutions. Okay. Okay, Ginny.
Yeah, yes.
Okay. Effects of area change on flow properties. An ideal gas is flowing through a constant area duct. The nature of the flow is defined as steady, isentropic, and one-dimensional. Which parameters remain constant for this flow? Yes. It's a MSQ type question. MSQ type question. Multiple select. Yes. Please answer. Try to answer. It's a constant area duct. All right.
One is Mach number.
Yes. Mach number. What will remain constant? Okay, Mach number will remain constant. Then, if Mach number remains constant, then what? Velocity will also remain constant, isn't it? If velocity remains constant, pressure will also remain constant, isn't it? And what happens to enthalpy? They have given it's isentropic. There is no entropy change. Also, because there is no velocity change, enthalpy is also constant. All right. And what happens to temperature and density? Because it's a constant area duct. All right. So these static conditions, temperature and density will also remain same. Okay. All right. No change.
Sorry,
But if you
everything will not. I think only
yes,
C and D.
sorry.
Because I think only C and D will not change. Velocity and
Uh,
pressure enthalpy will also go.
why velocity will change? Yes, Yogesh?
It will be flow now. I think it will change
So
in that.
no, we have, first of all, we have said the flow is steady, all right?
uh,
And
flow is
why,
flow is steady
why,
means density.
no,
Because flow is
okay,
steady means density will not change. That is the thing we take basically in
right,
ink
right,
print.
right, right, right. But also, if we don't consider friction, right, how is the flow supposed to retard? Because in if you see blast waves, there is obviously retardation. But if we see ideal conditions, all right, which is this case, like this is isentropic, okay. In that scenario, because if you say C also, if temperature is not changing, right? So if you are saying Mach is not changing, all right, what is Mach? Mach is velocity by A, all right. If temperature is not changing, then A will also not change. And if there are no friction effects, all right, then this will also not change. Why would it change?
Yeah, in that way it will not.
Hmm. Okay. All right. Okay, we are out of time now. All right. So I have last question, so I'll just discuss that. All right. Okay. So last question is, let's just check this out. Fill in the blank type of question, and then we are done with the session. All right. Quickly, a steady one-dimensional flow in the absence of dash and dash is called as isentropic flow. It's the definition of isentropic flow. Yes.
Heat transfer and body force.
Hmm. What does Ginny say? No answer. All right, all right. So I'll just okay. That is fine. That is fine. So Yogesh is correct in this question, all right. So heat transfer and body forces. I believe this is from the one of the slides content, all right. So heat transfer for isentropy, there must not be any heat transfer, and body forces should not come into picture. All right. So A is the answer to this question. Okay, then we are done with today's session. In the today's session, week 3 session, we discussed some problems based on quasi-static 1D flow. All right. And in this session, we included one new idea, that is to uh, do questions based on the topics that have been discussed. So I'm just trying to do justice with the concept of this taking live tutorial sessions. All right. So I hope we succeed in this particular thing. All right. And in that fashion only we concluded we this today's session. And with this, I conclude today's session. All right.
Sir,
And
only one thing.
yes, yes,
There are 4 books given to for reference. In which book we can refer? Basically, there are 4 books given.
yes.
One is
Okay.
Ethirajan's one and
See, for yes, when
John
see,
Anderson one, Ethirajan one.
I have like gone through this. I have referred to two books, all right. One, Anderson, like I really like Anderson because for beginners it's very feel good type of writing Anderson has. So that I like about Anderson, but also in my bachelor's, like this the supervisor for this internship, the scientist had that time recommended me E. Radhakrishnan. So that time I refer to that book. So if you like ask from me, like I have gone through, like I have referred to these books, but it's about your taste also, like which type of reading you prefer and what content you want to go through this. What you can do is just go through the contents of the book first, right? So I do it this way, like I first go through the contents, and then based on contents, if I find something that is in my mind that I want this from the subject, and I find the topics in that fashion, so I take a call that okay, I can use this as a reference for my whole course. Okay, but don't just use all the references. One or two references should suffice. Okay.
Okay, sir. Thank you.
Yes. All right. Okay then. We shall meet in next session. Sorry.
Thank you.
Okay then. Bye bye. Thank you. Happy learning. Take care. Bye.
Thank you, sir.
Thank you.